Next, let's look at page 410, where we have the chain rule of two independent variables. The previous one we did where x is or y is in terms of t. What if it had in terms of two things instead of just one? Let's say x is some function in terms of u and v, and so is y. And then how does the chain rule work when you plug everything into the function f? Well, it works the same way as the first one. And like this, and in a very symmetrical, pleasant pattern that's easy to remember. For example, if you need partial c to partial u, you will take, first you do the x one, okay, partial c, partial x, partial u, and then do the y one, do each one. And the same with partial c, partial v. So you have a symmetrical equation that helps you remember it. And so with that, please do example 4.27 as part of your homework when you practice taking derivatives again. And next, go to the next page, 412, we have the generalized chain rule. That is, if you have a function that has a large number of variables, we don't know how many, x1 to xm, okay? And then you have, and each one of those variable is dependent on some other variable, where ti to tn, okay? So now how do you do the partial derivatives? Now that might sound complicated at first, but it's not as complicated as it sounds. And you do the same thing as we've done before. So I have written down here, let's see you have a function with who knows how many variables, okay? And it goes all the way up to m, but it's finite. And then you have, and each one of these variables are functions of some other variables, okay? N of them, who knows how many, but it's a finite, it has n variables. So then how do we take the partial derivative? What you do is you do it one by one. For example, let's say we want to take the partial derivative of w, okay, to t1. Let's start with t1. All right. So what you're going to do is you are going to imagine yourself, you're like the king in a country, and you want to tax the people. Okay. The people have various objects, apples, oranges, pears, etc. And you want to tax, in this case, first you want to tax them on their apples. All right. So what you're going to do is you're going to go into each household and take an apple, take their share of apple out of them. Okay. So here's what you're going to do. You go to the first household, that's partial x1. Okay. That's the first household. And then you take out their tax, their apple tax. So partial x1, partial t1, because t1 is what we're doing. And then you go to the second household and do exactly the same thing. You take the derivative with respect to the second household. So partial partial x2. x2 is the second household in your kingdom. And then you tax them on the orange. So the second household has to pay the orange tax. What was it? I said apple. Never mind. Apple tax, okay, T1. And you keep going that until you go to every last household in your kingdom and tax them for the apple that you want. Partial XM, okay, and tax the XM household for the apple, okay, T1. T1 is apple. And so that's how you take the derivative of T1. Partial derivative of the w against t1. You just go through every single household, okay, one at a time. So x1, x2, all the way to xm that you take the partial derivatives, and each household will give you their taxable share of apples. So each one you tax t1, so each household, this is household 2, right? Okay, but each household will give you a tax of apples. So each household you take derivative with respect to T1 because that's what you're taxed, what you're going for. Why do you want so many apples? Who knows? You're the king. You know, kings are nuts. But anyway, so in general, if the king wants something, let's call it Ti. Okay, whatever I might be, doesn't matter. And if the king wants Ti, any object. So then what he does is he goes to each household and tags the household for that object, each one, every single one of them. See, this is the king's household, right? And this is each household, what they have, all the items they have that's taxable. And so what you do is you plug the xi into each function, and this is an unofficial way of me writing it. This is just x1 t going from 1 to n. So I write it this way, okay? I just made this up. It might be the normal way of saying it. It might not be, doesn't matter, but you get my idea. We'll plug it in, and then you take the derivative of whichever one item that you want, okay? That is, you take the partial derivative with whichever variable you want by taking the partial derivative of each original household, and, okay, and then multiply by the household's share of the specific item that you're taxing. And that taxing, that's how you would remember the partial derivative. The partial derivative formula is completely symmetrical. You just go through each one and go for the item that you're shooting for. Go to each house and find it. And the book mentions some kind of a tree formula, which that doesn't sit well with me, okay? But everybody's different. If the tree formula makes better sense to you, then by all means go after that. This is how I would recommend that you remember it. And in fact, I don't even recommend you remember it. If you need to know the chain rule and can't remember it, just look it up. What's the big deal, right? So having said that, please do example 4.28 as part of your homework. Do I have that here? Let's see. Yep. And then, I'm going to skip 4.29 because they want you to draw the tree, which I think is, I'm not drawing any trees. It's just a formula. Look it up if you can't remember it. And let's move on to page 416, where we look at the implicit form differentiation. We can't get out of the implicit differentiation, right? Now the implicit differentiation, let's look at the formula for a second, is similar to the regular implicit differentiation of calculus 1, and we don't care about that either. We just plug this in, okay? Here is the implicit differentiation. If you have just one variable or something, then the implicit, what do I mean by that? Well, whatever. If z is fxy, okay, then dy by dx is the same as partial negative partial f partial x partial f partial y, and then if there's more variables, if that is you have 3 variables, then you have partial c partial x and so on, and they're all negative. Now we're going to show what that means in a second. We're going to prove it, okay? So what happens is that you have, let's see. Actually, I think I'm going to backtrack and explain what I'm talking about first. Okay, now let's say you have an equation where f of x, y equal to 0. And then we don't know, we want to figure out dy by dx. Okay, what is dy by dx? But this function doesn't have y plugged out of it explicitly. So to calculate dy by dx, then there's a way to do this, and that is the equation given here, which we will prove in a second. See, right here, dy by dx will end up being partial f partial x divided by partial f partial y negative. And similarly, if you have a function that has 3 variables, f, x, y, z equal to 0, and then somehow z is in here, okay, and you want to figure out what partial z by partial x is. In that case, it will equal to and by the time we get through the proof, then you realize that it is equal to partial f partial x and partial f partial c, and that will end up with partial z, partial x, you notice the fraction makes sense. That is, if you flip that around, that kind of evens out. But that's not the point. The point is that that formula works, and we're going to prove it. First, let's prove the first one, which is dy by dx is equal to the negative of partial f. I should write it down. Is equal to negative partial f partial x divided by partial f partial y. Now, the reason we do it this way is because we can't plug y in terms of x very easily. You know, maybe y is in some big complicated mess, and we can't yank it out. So then we do, but even then we can calculate the derivative by this trick, negative sign. Don't forget the negative sign. Yes. Okay. So having said that, let's see how that is proved. The proof goes like this. Okay, now I will show you the proof of this one. The proof on the following page, it says that because f of x equal to 0, okay, it's just an equation that equals to 0. So then, then we take the derivative of both sides, then with respect to x, then we get that equal to 0. So then this derivative is applying the chain rule, we get this thing. Okay, and then in here there is a dy by dx. Now dx by dx is just 1. So then we get this thing, which from this equation, then we pluck dy and dx out, then you directly get to this result right here. Did I have a negative sign? Yeah, it was right here. It's hard to see, but it's right there. And so that's how that equation is derived. Now, what about the one with 3 variables? Now, the book has skipped that, so I decided to write it down. Let me find it. So to apply the exact same trick as the previous proof, we know that f x, y, z equal to 0, and we're looking for partial z over partial x. Now, how will we do that? First, we notice that because this equation is 0, then if we take the partial derivative with respect to x, right, it's just taking the derivative of 0, which is 0. All right, so far so good. And this thing, so as a result, what is partial f partial x? We apply the chain rule. So it becomes partial f partial x, let's see, yes. You take derivative with the x1, okay, and then take derivative with the y1, and take derivative with the z1. Just like just like before. Now, once we did this, then we look at this thing and we realize that partial x, derivative of x with itself is just 1, okay? Derivative of y with x is 0. The reason is because y is for the partial derivative. When you take partial derivative, the other variable don't matter, okay? And so, I mean, it's just a constant to you, right? So this derivative is 0, and then partial z partial x is what we're looking for, because we're pretending that z is a function of x and y, but we just can't figure out what it is. So then we have this situation where this thing is 0. This thing is just partial f partial x. So when you plug partial z partial x out of this mess, then you get the negative of partial f partial x, negative, divided by this, let's see, right here, partial f partial c. Doing the basic equation, and that's where you get this formula as shown in the book. And partial z partial y, it works exactly the same way. Just replace x with y, and that's how this part is proven. So with that, please do example 4.30 as part of your homework. And so we have come to the end of this section, differentiation, the good old chain rule, right? Can't live without it. So let's see, what am I doing? Okay, so let's get to the homework. Now for homework on page 419, please do problems 215, 19, 23, 27, 29, 33, 37, 41, 45, 49, 51. And I'm not going to go over any of it because they're all straightforward, and some of them take a long time. But I think most of them are actually pretty good. The book is being very nice to you and not making you work too hard. So most of the problems I think are fairly straightforward and might not take as long as the examples. The examples are actually harder. But anyway, so please do your homework, and that's the end of this section.